there is no true emptiness between the stars. Even in the long stretches where no planet turns and no sunlight falls strongly enough to warm a surface, matter is still present. It may be spread so thinly that a room on Earth would seem crowded by comparison, but it is there. Hydrogen atoms move through the dark. Tiny grains of carbon and silicate cross the galaxy. Charged particles spiral along magnetic fields. Waves of pressure pass through clouds that can take millions of years to change their shape. This is the interstellar medium, the material that fills the space between one star system and the next. From Earth, those distances can look like clean gaps. A bright star appears here, another there, and the blackness between them seems unoccupied. But the Milky Way is not a collection of isolated lights suspended in nothing. It is filled with a changing mixture of gas, dust, radiation, magnetic fields, and high-energy particles. Some regions are colder than any winter on Earth. Others are heated to temperatures of millions of degrees. Some are dense enough to become the beginnings of new stars. Others are so thin that a single atom may travel a long distance before striking another, and none of it remains perfectly still. The galaxy turns. Stars move through it. Supernova explosions send expanding shells into surrounding space. Young stars blow winds into the clouds where they formed. Gravity gathers material inward, while radiation and shock waves push it outward again. The result is not a motionless haze, but a slow circulation of matter across enormous distances. The atoms moving between the stars have often lived many lives already. Some hydrogen has remained almost unchanged since the early universe. Heavier elements were formed inside stars and scattered outward when those stars lost their outer layers or came apart. Dust grains assembled from this enriched material, carrying carbon, oxygen, silicon, iron, and other elements into new regions of the galaxy. Over time, those same ingredients may enter a cold cloud, become part of a new star, settle into a disk, and join the body of a planet. The calcium in bone, the oxygen moving through the blood, and much of the carbon in every living cell belong to this long galactic exchange. Before they became part of Earth, their atoms traveled through the space between stars' skies. Tonight, the journey begins inside that moving space. It will pass through thin clouds that are almost impossible to see, through dense molecular regions where starlight is absorbed, and through hot cavities shaped by stars that no longer exist. It will follow dust as it blocks light, glows in infrared wavelengths, and helps gas cool. It will move with magnetic fields that cannot be seen directly, yet guide charged particles across the galaxy. And it will come close to the small region surrounding our own solar system, where the sun meets the material flowing past it. The space between stars is not a single environment. It is many environments overlapping, exchanging matter and energy, changing one another over time. From a distance, the Milky Way may seem stable, its pale band crossing the night sky in the same familiar arc. Within it, however, material is always moving. Clouds gather, cavities widen, old stars return matter to space. New stars begin inside what previous generations left behind. The galaxy carries its history in this circulation, and in the darkness between its lights, the next generation is already taking shape. The first clues were not found by traveling into interstellar space. They were found in starlight. For much of human history, the dark markings across the Milky Way could be understood only as absences. In a sky crowded with stars, certain regions seemed strangely blank. Some observers imagined openings in the star field, places where the galaxy itself had thinned. Others suspected that something lay in front of the distant light. Photography began to settle the question. During the late 19th and early 20th centuries, long exposure plates revealed dark lanes with edges too defined to be simple gaps. The American astronomer Edward Emerson Barnard photographed many of them in careful detail, Against the bright background of the Milky Way, they appeared as black islands and winding channels. Barnard came to understand that these were not empty holes, they were clouds, nearer than the stars behind them, hiding the light. A dark cloud becomes visible by refusing visibility. It may produce little light of its own, at wavelengths the human eye can see. Instead, dust grains within it absorb and scatter the light arriving from farther away. The cloud is traced by the stars that disappear behind it, much as an unseen object in a bright room can be recognized by the shadow it leaves on a wall. This effect is called extinction. It does not remove every color equally. Small interstellar grains scatter shorter, bluer wavelengths more strongly than longer, redder ones. As starlight passes through dusty space, it can become both dimmer and redder. A star behind enough dust may look cooler than it really is, or may vanish from an ordinary photograph altogether. By comparing its observed light with the light expected from its type, astronomers can estimate how much material lies along the path. The darkness between stars had begun to show its shape. Gas revealed itself in another way. At the beginning of the 20th century, the German astronomer Johannes Hartmann studied the spectrum of Delta Orionis, one of the stars in Orion's belt. The star is part of a binary system, and its spectral lines shift as the stars move in their orbit. Yet narrow lines made by ionized calcium did not move with them. They remained nearly fixed. The calcium could not be traveling with the star. It had to be somewhere between the star and Earth, resting in a separate cloud through which the light was passing. The star had become a lamp placed behind invisible gas. Its spectrum carried the imprint of matter that no telescope could photograph directly. This is one of astronomy's most useful arrangements. A distant source provides the light. Intervening material alters it. A spectrograph separates the arriving light into wavelengths, and the missing portions reveal which atoms or molecules absorbed them. Hydrogen leaves one pattern, sodium leaves another. Calcium, carbon, oxygen, and many other elements leave their own narrow signatures. The position of each line identifies the substance. The slight shift of the line shows whether the absorbing cloud is toward or away from us. Several lines at slightly different shifts can reveal several clouds lying along the same view, each crossing the path at its own speed. A single star can therefore illuminate an entire column of galactic space. What looks like one uninterrupted distance may contain a sequence of environments. A nearby veil of diffuse gas, a colder cloud farther on, and another moving layer closer to the star. They overlap in the sky, but spectroscopy separates them by motion and chemistry. Some features remain less easily explained. In the early 20th century, astronomer Mary Leah Hager recorded broad absorption marks in the spectra of distant stars. These features did not belong to the stars themselves. They appeared only when enough interstellar material lay in front of them. They became known as diffuse interstellar bands. Hundreds are now known, and many of their carriers remain unidentified. A small number have been linked convincingly to a large carbon molecule called ionized Buckminster fullerene, shaped like a hollow cage. Most of the bands still wait for secure chemical names. Their presence is a reminder that even thin interstellar clouds contain a chemistry more varied than the darkness suggests. Visible light provides only one layer of the view. Dust that hides stars in optical wavelengths absorbs their energy and releases much of it again in the infrared. A region that looks black to the eye may glow when observed by an infrared telescope. Colder material can be traced at far infrared and sub-millimeter wavelengths, where faint thermal effusion from dust reveals filaments, clumps, and broad sheets crossing the galactic disk. Radio telescopes add another map. Neutral hydrogen can emit radiation at a wavelength of about 21 centimeters. This signal passes through dust that blocks visible light, allowing astronomers to trace atomic hydrogen through much of the Milky Way. Carbon monoxide is often used to locate denser molecular regions where hydrogen molecules are abundant but difficult to observe directly under cold conditions. No single instrument sees the interstellar medium as a whole. An optical telescope notices what has been hidden. A spectrograph notices what has been removed from the light. An infrared observatory detects the warmth of dust. A radio dish listens for atoms and molecules. Measurements of polarization show how dust grains align with magnetic fields. High-energy observatories find hot gas left by shocks and stellar explosions. Each method reveals a different condition of the same galactic material. The resulting maps do not resemble a smooth fog. They show threads, shells, cavities, knots, and overlapping layers. Some structures extend across only a fraction of a light year. Others span hundreds of light years. Their boundaries are shaped by gravity, turbulence, radiation, magnetic pressure, and the motion of stars through the disk. Modern surveys can compare millions of stars at known distances, building three-dimensional maps of the dust between them. A nearby star may appear almost untouched, while a farther star in the same direction is strongly reddened. The change marks where a cloud begins. Repeated across the sky, these measurements turn scattered lines of sight into a layered map, allowing astronomers to place obscuring structures within the galaxy rather than seeing them only as flat shadows. You might picture the night sky as a dark window filled with points of light, but every point reaches you through a path. Along that path, matter may dim it, redden it, divide its spectrum, or leave a signature too faint for the eye to notice. The space between stars does not announce itself directly. It becomes known through what it changes. There is another layer here, one that does not divide interstellar space by distance, but by condition. A cloud can be cold enough for atoms to remain neutral. Nearby, another region may be thousands of degrees warmer, with electrons separated from their nucleus. Beyond both, gas, heated by a stellar explosion, may reach 1,000,000 degrees while remaining so thin that it contains very little matter at all. These environments are often called phases of the interstellar medium. The word phase may bring to mind water changing from ice to liquid to vapor. Interstellar phases are not quite so orderly. Their boundaries can overlap, fold, and move. Gas may pass from one condition to another as it is compressed, illuminated, shock shielded, or allowed to cool. Hydrogen provides the simplest guide. In the cold neutral medium, much of it remains in the form of individual atoms. Temperatures are often near 100 kelvins, sometimes lower, and the gas is denser than the warmer material around it. Dense in this setting is a relative word. A cubic centimeter may contain a few dozen particles, a number still far below anything experienced as ordinary air. Yet across a cloud many light years wide, even that thin population adds up. Cold atomic gas often appears in sheets and narrow filaments. It can absorb the 21 centimeter radio emission coming from warmer hydrogen behind it, leaving dark features in radio maps. The cloud may be nearly invisible to the eye, but at the right wavelength, its lower temperature becomes a signature. Where the gas is more exposed to starlight, a warmer neutral phase can persist. Here, hydrogen atoms remain mostly intact, but their motions correspond to temperatures of several thousand degrees. The material is much more diffuse than the cold phase. A particle may travel a considerable distance before another comes near, and the gas spreads through broad portions of the galactic disk. Cold and warm neutral gas can exist under similar surrounding pressures because temperature and density trade places. In a warmer region, particles move more rapidly but are spaced farther apart. In a colder region, they move less rapidly but are packed more closely together. The pressure produced by one can resemble the pressure produced by the other, allowing sharply different conditions to remain beside each other for long periods. The balance is not perfect. Not every parcel settles into one of these familiar ranges. Some gas occupies intermediate temperatures while it cools from a shock or mixes across a boundary. Some is driven away from thermal balance before it can adjust. The phase names are useful because they describe recurring conditions, but the real galaxy contains continua, transitions, and structures too small or too brief to fit neatly into a few categories. This uncertainty does not make the model useless. It makes the motion more important. A phase is best understood not as a permanent address, but as one portion of a route through pressure, temperature, density, and ionization. Turbulence bends the boundaries. Shock waves compress one side of a cloud. Radiation heats an exposed surface while the interior remains protected. Magnetic fields resist motion across certain directions. Gravity becomes important in the densest regions, gathering material beyond the balance that supports the more diffuse gas. The interstellar medium is therefore not a tidy collection of containers. It is a landscape of temporary agreements. Heating and cooling help decide which agreements can last. Ultraviolet light from stars can release electrons from tiny dust grains and large carbon-rich molecules. Those energetic electrons collide with the surrounding gas and share some of their energy. Cosmic rays penetrate regions that ordinary starlight cannot easily reach, ionizing atoms and contributing heat. X-rays, shocks, and the motion of charged particles add energy in other places. Cooling occurs when particles collide and leave atoms or ions in excited states. As those states settle, they release photons. The photons escape, carrying energy away from the gas. Carbon, oxygen, and other trace elements can be powerful cooling agents, even though hydrogen and helium make up most of the material. A change in density can shift the balance. If a parcel of gas is compressed, collisions become more frequent. Cooling may become more effective, allowing the temperature to fall. The falling temperature can permit further compression. Under the right conditions, warm diffuse gas can move toward a colder, denser state, gathering into strands and clouds without any single moment when the transformation begins. The reverse can happen as well. A shock may pass through cold gas and heat it. The newly formed star may illuminate the cloud around it. Particles that once moved slowly begin to move faster. Molecules may separate, and atoms may lose electrons. Matter that had settled into one phase returns to another. Around hot young stars, ultraviolet photons can ionize large regions of hydrogen. An ionized hydrogen region is not simply warmed gas. Its atoms have been altered. Electrons move freely among positively charged nuclei, creating a plasma that responds to electric and magnetic forces. When electrons reunite with nuclei, the gas emits characteristic light, including the red hydrogen glow seen in many emission nebulae. These regions often look like bright blossoms around the stars that power them. Their edges mark the distance at which the supply of ionizing photons can no longer keep most of the hydrogen separated. Beyond that boundary, neutral gas may continue outward, carrying a different temperature and chemistry. A more widespread warm ionized medium extends far beyond the bright nebulae. It is faint and diffuse, threaded through the Milky Way in layers and irregular structures. Pulsars help reveal it. Their radio pulses travel through free electrons on the way to Earth, and lower radio frequencies are delayed slightly more than higher ones. Measuring that delay gives astronomers a record of the electrons along the path. Even an almost invisible plasma leaves time behind in a signal. The hottest interstellar gas occupies another part of the cycle. Supernova explosions and powerful stellar winds drive shocks into surrounding material. Behind a fast shock, particles can be heated to hundreds of thousands or millions of degrees. At such temperatures, atoms are highly ionized, and the gas can emit ultraviolet radiation and soft X-rays. Calling this gas hot can be misleading when translated into human sensation. Temperature describes the typical energy of individual particles. It does not tell us how many particles are present. In hot interstellar cavities, the particles may carry great energy, but they are spread so widely that there is little material available to transfer that energy to an object passing through. A thermometer placed there would not experience anything like a furnace. The gas is hot in particle motion and sparse in substance. It can fill a large volume while accounting for only a small share of the interstellar mass. Vast cavities may remain after several supernovae have expanded through the same stellar neighborhood, their interiors rarefied and their boundaries outlined by cooler shells. The solar system lies within such a broader region, commonly called the local bubble. This low-density cavity extends for hundreds of light years in an uneven shape. It was likely influenced by multiple supernova explosions over millions of years. Within it are smaller clouds of warmer material, including the local interstellar environment through which the Sun is now moving. So even our nearby surroundings contain several conditions at once. The Sun creates its own protective region through the solar wind, while outside that boundary lies interstellar plasma, neutral gas, dust, magnetic fields, and cosmic rays. The heliosphere moves through this material. As the Sun orbits the center of the galaxy, the border is not a wall, but a changing interaction between two flowing media. On larger scales, the phases of the interstellar medium are continually rearranged. Cold clouds gather mass. Warm gas fills the spaces around them. Ionized regions expand from young stars. Hot bubbles rise and overlap. Material can leave the thin galactic disk, cool at greater height, and later return, carrying metals and energy through a slow circulation. No region keeps one identity forever. A hydrogen atom may spend millions of years in warm neutral gas, enter a compressed filament, join a molecule in a shielded cloud, become ionized beside a new star, and later be swept into a hot, expanding shell. The atom remains hydrogen, but the environment around it changes its motion, its partners, and the light it can absorb or release. The space between stars is filled not by one substance in one state, but by matter passing through conditions, and every condition prepares the way for another. The boundaries between these regions are rarely smooth. They are folded by motion. Gas in the Milky Way does not simply expand from one place and settle quietly in another. It is stirred across scales so different that a small disturbance can belong to a much larger pattern. A passing shock compresses a cloud. A cluster of young stars drives material outward. A supernova pushes a shell through surrounding gas. Galactic rotation stretches structures along the disk. Gravity draws denser regions inward, while nearby flows shear them apart. Together, these motions create turbulence. On Earth, turbulence appears in smoke curling above a flame, in water passing around a stone, and in air shifting behind an aircraft. The details change constantly. Large swirls break into smaller ones. Smaller motions pass energy downward through a sequence of scales until that energy is finally converted into heat. Interstellar turbulence follows some of the same broad principles, but the setting is different. The gas is often extremely thin. Much of it is electrically charged. Magnetic fields run through it. Motions can be faster than the local speed of sound, producing shocks rather than smooth pressure waves. Cooling can change the temperature before a flow has time to settle. Gravity may begin gathering the densest pieces, even while the larger cloud continues to churn. The result is a medium that is structured without being planned. A cloud that looks solid in a distant image may be composed of filaments, sheets, knots, and cavities. Some parts move toward one another, others slide past. A dense ridge may have formed where two flows met, while a nearby pocket may be opening as material streams away. These structures are not merely decorative details. They influence where gas becomes dense enough to form molecules, where radiation can penetrate, where dust can survive, and where gravity may eventually gain control. In a cold molecular cloud, turbulence can support material against collapse for a time. Random motions provide pressure, preventing the entire cloud from falling inward at once. Yet those same motions also create compressions. Gas gathers along narrow intersections, and local density rises. Turbulence can therefore delay collapse on one scale while encouraging it on another. This double role is one reason star-forming clouds are difficult to describe with a single cause. Gravity matters, temperature matters, magnetic pressure matters, turbulence matters. Their influence shifts from place to place and from one moment to the next. There is no central mechanism arranging every filament. The cloud develops through the interaction of many forces, each responding to conditions that are already changing. Some of the longest filaments seen in molecular clouds extend across dozens or even hundreds of light years. Within them are smaller strands, and within those strands are denser cores. The arrangement resembles a branching pattern, but it is not fixed like the branches of a tree. Material can flow along the filaments, collect at their intersections, or be pulled apart by nearby activity. Observations of molecular spectral lines reveal this movement. When gas approaches, its emission shifts slightly toward shorter wavelengths. When it recedes, the shift goes the other way. Different velocities appear as different components in a spectrum. By mapping those changes across a cloud, astronomers can trace gradients, converging flows, expanding shells, and overlapping structures. The cloud becomes a field of motion rather than a flat image. Yet, velocity alone does not explain what guides the charged part of the gas. For that, another invisible structure must be included. The Milky Way carries a magnetic field. It is far weaker than the magnetic field near the surface of Earth, but it extends across distances so large that its influence becomes important. In diffuse interstellar space, charged particles spiral around magnetic field lines. Their freedom of motion is greater along the field than across it. As a result, the field can guide flows, resist compression in certain directions, and shape how energy moves through the gas. Magnetic fields do not behave like rigid wires. They bend, twist, and fluctuate with the plasma around them. Under many interstellar conditions, the charged gas and the field are coupled closely enough that motion in one alters the other. A flow can stretch a field line. A compressed region can strengthen the local field. Magnetic tension can resist bending, much as a stretched cord resists being displaced. But there is no cord in space. The comparison is only a way to picture how a field can carry tension without being a material thread. Astronomers infer these fields through several methods. One comes from polarized starlight. Interstellar dust grains are not perfect spheres. Many are elongated, and their alignment is influenced by the local magnetic environment. When light passes through a region containing aligned grains, one orientation of the light is absorbed more strongly than another. The remaining light becomes polarized. Across many stars, those polarization directions reveal the projected orientation of the magnetic field on the sky. Dust itself can also emit polarized radiation at far infrared and submillimeter wavelengths. Maps of this emission show field patterns curving through clouds, following some filaments and crossing others. In certain regions, the field appears orderly. In others, turbulence has tangled it into more complex shapes. Radio waves provide another path. When polarized radiation passes through ionized gas threaded by a magnetic field, its polarization angle rotates. The amount of rotation depends on the number of free electrons, the strength of the magnetic field along the line of sight, and the wavelength of the radiation. This effect, called Faraday rotation, allows astronomers to examine magnetic structure through the galaxy. pulsars are especially useful. Their signals begin highly organized and travel across long interstellar paths. The delay between radio frequencies measures the free electrons encountered, while the rotation of polarization measures the magnetic influence along the same route. Together, these observations help separate density from field strength. Zeeman splitting offers a more direct measurement in certain environments. A magnetic field can divide an atomic or molecular spectral line into closely spaced components. The separation is extremely small, but when it can be measured, it provides information about the field along the line of sight. Such observations are difficult and limited to suitable species and conditions, yet they give valuable constraints within dense clouds and atomic gas. No method provides the complete three-dimensional field. Each reveals one portion, a direction projected across the sky, a component along the line of sight, or an average across a long path. Reconstructing the magnetic structure of the Milky Way requires combining these partial views. The result is a galaxy threaded on several scales. There is a broad field associated with the galactic disk, influenced by rotation and large-scale flows. Superimposed on it are loops, compressions, and irregularities created by turbulence, expanding shells and local clouds. In some places, the field helps organize matter into elongated forms. In others, the motion of the gas appears strong enough to distort the field. Neither side always dominates. In diffuse regions, magnetic pressure can be comparable to thermal and turbulent pressure. Within a dense cloud, gravity may become stronger as material accumulates. Yet, even there, the field can slow motion across certain directions, changing the shape and timing of collapse. The relationship becomes more subtle in mostly neutral gas. Neutral atoms do not respond directly to magnetic fields, but they collide with the ions and charged dust grains that do. Through these collisions, the neutral material can remain partly coupled to the magnetic field. The coupling is not perfect. Under certain conditions, neutral matter can gradually slip past the charged component. This process, known as ambipolar diffusion, allows material to move across field lines over long timescales. It was once considered a central route by which magnetically supported clouds could begin collapsing. It remains part of the physics, though observations and simulations suggest that real clouds are also shaped by turbulence, rapid compression, changing ionization, and complex field geometry. The importance of ambipolar diffusion varies with the environment. Interstellar motion rarely offers one universal answer. Even the idea of a field line must be handled with care. Field lines are a visual tool used to represent direction and strength. They are not separate physical strands occupying space. When astronomers speak of particles following a field line, they mean that the local field shapes the particle's path. When they describe a field as tangled, they are describing how its direction changes from place to place. The actual field fills the region continuously. Cosmic rays respond strongly to this structure. Most cosmic rays are high-energy atomic nuclei, especially protons, moving through the galaxy at speeds close to that of light. Because they are charged, they do not usually travel in straight lines from their sources to Earth. Galactic magnetic fields bend their paths, scattering and redirecting them many times. This makes their origins difficult to trace. A cosmic ray reaching the solar system may have wandered through the Milky Way for millions of years, its route folded by magnetic irregularities. The direction from which it arrives does not necessarily point back toward the event that accelerated it. Many are thought to gain energy in the shock waves of supernova remnants, where expanding magnetized plasma can repeatedly scatter particles across a moving shock. Other sources may contribute, especially at the highest energies. Once released, cosmic rays become part of the interstellar environment. They penetrate deep into clouds, where ultraviolet starlight has been absorbed. There, they can ionize atoms and molecules, beginning chemical reactions that would otherwise proceed very slowly. They also provide a modest source of heat within shielded regions. Their presence connects violent events with cold molecular interiors. A supernova may occur far from a cloud, yet particles accelerated by its shock can eventually enter that cloud and alter its chemistry. Magnetic fields guide the route. Turbulence changes the route. The cloud receives energy without receiving visible light from the original event. This is one of the quieter forms of galactic connection. Matter, radiation, fields, and particles do not remain confined to the places where they began. They travel, scatter, mix, and return in altered forms. The magnetic field also carries waves. When plasma is disturbed, changes can move through the field and gas together. Some of these motions are called magnetohydrodynamic waves. They transport energy and contribute to turbulence. They can scatter cosmic rays, influence heating, and help distribute disturbances across regions that would otherwise seem disconnected. In a medium this thin, a disturbance may continue across an enormous distance before fading, but it does not move through an unchanging background. Density varies, temperature changes, the field turns. Waves reflect, steepen, interact, and break into smaller motions. The galaxy is full of movement, layered upon movement. A large flow crosses a cloud. Turbulence divides it. Magnetic fields redirect part of it. Shocks compress the gas. Cooling changes the pressure. Gravity takes hold where enough material gathers. From far away, the result can look almost motionless. A dark cloud may appear fixed against the stars for an entire human life. A filament may keep the same shape through every photograph taken across decades, yet its internal crossing time may be measured in hundreds of thousands or millions of years. The motion is real, only stretched beyond ordinary patience. You are seeing one frame from a process that does not need to hurry. Within that frame, gas slides along fields, particles scatter through magnetic irregularities, and compressed regions wait beneath the balance of pressure and gravity. The space between stars is not only filled, it is being stirred. Among the moving gas are particles large enough to have surfaces. They are still far too small to see individually. Most interstellar dust grains are smaller than the width of a human hair, and many are smaller than the wavelengths of visible light. Yet these grains influence how the Milky Way looks, how its clouds cool, how molecules form, and how the raw material of future planets begins to gather. Dust is only a small fraction of the interstellar mass. Hydrogen and helium dominate the space between stars. But dust interacts with light so efficiently that it can shape our view of entire regions. A cloud containing relatively little solid material may obscure thousands of stars behind it, redden the light that passes through, and glow at wavelengths the human eye cannot detect. The grains are not all made from the same substance. Some contain silicate minerals built from silicon and oxygen, combined with elements such as magnesium and iron. Others are rich in carbon, very small carbon-based particles, and complex aromatic molecules contribute distinctive infrared emission when they absorb ultraviolet photons and release the energy through vibrations. The exact mixture changes from one region to another. A grain may begin in the atmosphere of an aging star, where cooling gas allows solid particles to condense. Another may form within expanding debris after a stellar explosion, though powerful shocks can also destroy much of the material being created. Once released, grains enter the interstellar medium and begin a long passage through radiation, collisions, magnetic fields, and clouds. Their survival is never guaranteed. Fast shocks can strike grains hard enough to break them into pieces. Energetic ions can chip atoms from their surfaces, a process known as buttering. Ultraviolet radiation can alter carbon-rich material. Collisions between grains may shatter them, while gentler encounters inside dense regions can cause them to stick together. A dust grain is therefore not a permanent object traveling unchanged through the galaxy. It can lose material, gain material, fragment, grow, and become coated in ice. The solids that eventually enter a forming planetary system may have passed through several stars and many interstellar environments before arriving there. In exposed regions, starlight keeps grain surfaces relatively warm and chemically active. In the interior of a dense cloud, the situation changes. Dust blocks much of the external ultraviolet radiation. The temperature falls. Atoms and molecules striking a grain can remain attached rather than immediately returning to the gas. Layer by layer, an icy coating begins to form. Water is one of the most important components, but the ice can also contain carbon monoxide, carbon dioxide, methane, ammonia, methanol, and other compounds. These substances do not arrive as a finished mixture. Some freeze directly from the gas. Others are assembled through reactions on the surface. A grain only a fraction of a micrometer across can become a meeting place for atoms that would rarely encounter one another in open space. This is especially important for molecular hydrogen. Hydrogen atoms are abundant throughout the galaxy, but forming a stable hydrogen molecule in the gas phase is difficult under ordinary interstellar conditions. Two atoms can collide, yet they need a way to release excess energy, or the new molecule will separate again. A dust surface provides that opportunity. An atom lands on a grain and moves across it. Another atom arrives. When the two meet, they can bond, and part of the released energy is transferred to the grain. The hydrogen molecule can then leave the surface and return to the gas. Across countless grains, this process converts atomic hydrogen into molecular hydrogen. The individual event is small. The accumulated result changes entire clouds. Molecular hydrogen is the main component of the cold, dense regions from which stars form. Yet it is surprisingly difficult to map directly. At the low temperatures found in many molecular clouds, it does not emit strongly at the wavelengths most commonly used to trace cold gas. Astronomers often rely on other molecules. Carbon monoxide is much less abundant than molecular hydrogen, but its rotational transitions produce radio emission that can be measured across large distances. By observing carbon monoxide, astronomers construct maps of molecular clouds and estimate how much hydrogen is likely to be present. The connection is useful, but not exact. Carbon monoxide can be broken apart by ultraviolet light in regions where molecular hydrogen survives through self-shielding. In other places, carbon monoxide may freeze onto dust grains and become faint even though hydrogen remains in the gas. Some molecular material therefore escapes ordinary carbon monoxide surveys. This hidden component is sometimes called dark molecular gas. It is not dark because it contains no radiation at all. It is dark in the sense that familiar tracers fail to represent it fully. Other signals, including emission from ionized carbon, gamma rays produced when cosmic rays interact with matter, and the thermal glow of dust help reveal what carbon monoxide alone misses. Every map is shaped by the tracer used to make it. A bright molecular line may identify one layer of a cloud while leaving another nearly absent. Dust emission provides a broader estimate of material but requires assumptions about grain, temperature, and composition. Extinction maps depend on background stars and become difficult in the most opaque regions. The interior of a cloud must be reconstructed from incomplete evidence. Even so, a recognizable pattern emerges. As shielding increases, hydrogen becomes molecular, carbon chemistry changes, temperatures decline, dust acquires ice. The gas begins to support molecules that would not survive in an exposed region. Some are simple combinations of only a few atoms. Others contain longer carbon chains or ring-shaped structures. More than 200 molecular species have been identified in interstellar and circumstellar environment that includes water, ammonia, formaldehyde, methanol, and molecules containing carbon, nitrogen, oxygen, sulfur, and silicon. Their presence does not imply biology. Chemistry can create considerable complexity without cells, metabolism, or reproduction. But it does show that the space between stars is not chemically inactive. Reactions occur in the gas. Reactions occur on grain surfaces. Ultraviolet photons break molecules apart and create reactive fragments. Cosmic rays ionize material deep inside clouds, allowing new pathways to begin where ordinary starlight cannot reach. An ion can attract a neutral molecule from a greater distance than two neutral particles might influence one another. This makes ion-molecule reactions particularly important in cold interstellar gas, where temperatures are too low for many reactions that require an activation barrier. Cosmic rays help maintain a faint level of ionization, even in heavily shielded interiors. A high-energy particle may strike a hydrogen molecule and remove an electron. The resulting ions react with other molecules, passing charge and rearranging bonds through a chain of encounters. From a small initial disturbance, a network of chemistry spreads through the cloud. The rate is slow by laboratory standards. A single reaction may occur only after a molecule has traveled for a long time through sparse gas. Yet a molecular cloud may persist for millions of years, and it contains an immense number of particles. Over that duration, rare encounters become a substantial chemical history. Time replaces density. Inside the coldest regions, chemistry can also become a measure of physical conditions. Certain molecules become more abundant when carbon monoxide freezes onto dust. Ratios involving deuterium, a heavier form of hydrogen, can rise at low temperatures. By observing these changes, astronomers estimate which parts of a cloud are coldest, densest, or closest to gravitational contraction. Molecules become thermometers, clocks, and records of hidden structure. Their spectral lines reveal more than composition. The width of a line reflects motion. Thermal movement broadens it slightly. Turbulence adds more broadening. A line with an asymmetric shape may suggest material moving inward or outward, though interpretation often requires several tracers because overlapping layers can produce similar patterns. Different molecules are most useful at different densities. One may trace the broad envelope of a cloud. Another appears mainly in denser filaments. Another becomes visible in compact cores where future stars may form. By combining them, astronomers move gradually inward through a region that visible light cannot enter. There is a patient quality to this method. No observer sees the cloud directly from within. No camera records the arrangement in ordinary colors. Instead, radio receivers collect narrow bands of emission. Infrared instruments measure the faint glow of cold grains. Spectra are compared, velocities separated, and chemical models tested against the signals. Generations of observers have added layers to the same hidden landscape. The first photographs showed dark patches where stars seemed to be missing. Later observations revealed molecular emission from those patches. Infrared surveys uncovered their dust. More sensitive instruments found dense cores, icy mantles, complex molecules, and fine networks of filaments. The darkness did not change. What changed was the range of light humans learned to notice. Within these clouds, dust also controls temperature. A grain absorbs visible and ultraviolet photons, warms slightly, and releases the energy in the infrared. In dense gas, collisions between particles and grains can exchange heat. At high enough density, the temperature of the gas begins to follow the temperature of the dust more closely. Cooling makes compression easier. When gas loses energy, pressure falls. Material can gather into smaller volumes without heating enough to stop the process immediately. Dust shielding protects molecules, and molecular lines help carry energy away. Together, these effects create conditions in which gravity can become increasingly important. But the path is not automatic. Many clouds disperse. Some are disrupted by radiation, winds, or shocks before they form stars. Some remain supported by turbulence or magnetic fields. Some contain dense regions that begin to contract while the surrounding material continues to move in other directions. A molecular cloud is not simply a waiting room for stars. It has its own evolving structure, chemistry, and internal weather. Star formation is one possible outcome within selected parts of it, not the inevitable fate of every parcel of gas. Dust grains participate in that selection. They shield the interior. They help create hydrogen molecules. They provide surfaces for ice and chemical reactions. They radiate heat away. Later, inside a collapsing core, they begin to collide and grow. The same grains that once darkened distant starlight become the seeds of larger solids in disks around young stars. Some of the material within a planet may therefore carry a history older than the star it circles. Certain presolar grains found inside meteorites formed around stars that existed before the Sun. Their isotopic compositions differ from material produced in the early solar system, preserving signatures of stellar environments that have long since disappeared. A microscopic grain can outlive its parent star, cross interstellar space, enter a new cloud, survive the formation of another star, and remain inside a rock for billions of years. Held in a laboratory, it becomes a fragment of the galaxy's circulation. Most interstellar grains leave no such recoverable record. They are altered, melted, broken, or rebuilt. Their histories become mixed into newer material until no instrument can identify where each atom last belonged. Yet the larger cycle remains visible. Stars manufacture elements. Winds and explosions return them to space. Dust condenses, travels, and changes. Clouds gather the grains. Chemistry develops on their surfaces. Gravity draws selected regions inward. New systems form from material, carrying traces of many older ones. The space between stars is where those generations meet, and inside its coldest clouds, matter begins preparing for a different kind of motion. In the densest parts of a cloud, motion begins to turn inward. The change may start inside a filament, where gas has been gathering for a long time. Turbulence presses material together. Magnetic support weakens in one direction. Cooling keeps the temperature low. A region that once shifted with the rest of the cloud begins to hold more mass than its internal pressure can comfortably support. Gravity does not arrive from somewhere else. It has been present all along, acting between every particle in the cloud. For most of the cloud's life, other influences have prevented it from taking control. Thermal motion pushes outward, turbulence stirs the gas. Magnetic fields resist certain kinds of compression. As density rises, that balance changes. A slightly denser region attracts more surrounding matter. The added material strengthens its gravity. The stronger gravity draws in still more gas. Under the right conditions, the process becomes self-reinforcing. The cloud has not yet formed a star. It has formed a core. Dense cores are among the smallest structures within large molecular clouds, though small remains a relative term. A single core may span thousands of astronomical units and contain enough material to form one star, a pair of stars, or a compact group. Some cores remain starless. They are cold, dark, and difficult to detect. Dust inside them emits faintly at far infrared and sub-millimeter wavelengths. Molecules in the surrounding gas reveal narrow spectral lines. Against brighter background emission, the densest centers may appear as shadows, even in the infrared. These cores are not motionless spheres. They contain gradients, internal flows, and uneven density. Some are elongated or threaded along filaments. Others show signs of contraction. A few may be temporary compressions that disperse before a star can form. But when gravity continues to gain influence, the center grows denser. Gas falls inward from many directions. As it moves, gravitational energy is converted into heat. At first, much of that heat escapes through radiation from molecules and dust. The collapse can continue, while the core remains cold enough for pressure to stay relatively low. The center becomes more difficult to cool as density increases. Radiation no longer escapes as freely. Matter begins to trap the energy released by contraction. The temperature rises, and a compact object forms within the surrounding envelope. This is the beginning of a protostar. A protostar is not yet powered by sustained hydrogen fusion in its center. Most of its early luminosity comes from the energy of infalling material and from the continued contraction of the growing object. The surrounding cloud feeds it. Material does not usually fall straight toward the center. Even a slowly rotating core carries angular momentum. As the core contracts, that rotation becomes more noticeable, just as a turning object spins faster when its mass is drawn closer to the axis. The infalling gas begins to flatten. A disk forms around the protostar. Within this disk, matter continues its journey inward, but angular momentum makes the route complicated. Gas circles the center rather than dropping directly onto it. Friction, turbulence, magnetic effects, and gravitational interaction allow some material to lose angular momentum and move inward. Other material carries angular momentum outward through the disk. The same physical constraint that helps create the disk also prevents all of it from falling into the star. This leftover material matters. Dust grains collide within the disk. Some encounters break them apart. Others allow them to stick. Tiny particles become larger aggregates, beginning a separate process that may eventually produce planetesimals, planets, moons, asteroids, and comets. A forming star and a forming planetary system therefore grow from the same rotating supply. The boundary between stellar material and planetary material is not decided at the beginning. It emerges gradually as mass moves through the disk, falls onto the protostar, becomes trapped in orbit, or is expelled from the system. Not all infalling matter reaches the center. Young protostars produce narrow outflows and broader winds. Jets can travel outward along the rotational axis, often extending far beyond the disk itself. They strike the surrounding cloud, creating shocks and luminous knots. The outflow seems to move in the opposite direction from the collapse, yet both processes belong to the same system. As material falls inward, magnetic fields and rotation help redirect a fraction of it outward. These outflows carry away angular momentum, making it easier for the remaining gas to continue moving toward the protostar. The growing star is fed by losing part of what approaches it. Across a star-forming cloud, many young objects may produce outflows at once. Their jets carve cavities, disturb nearby gas, and add new motion to the cloud. On small scales, an outflow may clear material away from its own protostar. On larger scales, overlapping outflows can stir the surrounding region. The cloud begins to be changed by the stars forming inside it. Before that influence becomes strong, the protostar remains hidden. Visible light from the center is absorbed by the surrounding envelope and disk. Infrared observations are more useful because longer wavelengths can pass through more of the dust. The absorbed energy also warms the surrounding grains, which then glow in the infrared. Astronomers classify young stellar objects partly by the shape of this emitted energy. The youngest stages are dominated by cold envelopes. Later, the envelope thins and the disk becomes more exposed. Eventually, the central star becomes visible, while a substantial disk remains around it. These categories describe a general progression, not a perfect clock. Viewing angle can change how a young system appears. A disk seen edge-on may hide the central object more effectively than the same disk seen from above. Different stars also evolve at different rates. and their environments can alter the sequence. Still, across large samples, the pattern reveals a gradual clearing. The protostar gathers mass, its interior temperature rises. Pressure increases at the center, resisting further compression. The object settles toward a state supported by internal heat rather than by the motion of the larger cloud. For a star similar in mass to the Sun, the contracting protostar eventually becomes hot enough at its center for hydrogen nuclei to begin fusing into helium. The energy released by fusion changes the balance. A main sequence star has begun. It may have taken hundreds of thousands to millions of years to reach this point. Depending on its mass and circumstances, more massive stars form more quickly. Lower mass stars take longer to contract. The interstellar material has become a source of sustained light. Yet the star does not simply detach from its surroundings. Young stars remain connected to their birth clouds through radiation, winds, disks, and gravity. Their ultraviolet light can heat nearby gas. Their outflows continue to disturb the cloud. If the star is massive enough, its radiation can ionize hydrogen across a broad region. An expanding ionized bubble pushes against colder material. The pressure difference can sweep gas into shells and pillars. Dense clumps resist erosion longer than their surroundings, leaving shapes that point toward the stars, illuminating them. Some compressed regions may collapse and form additional stars. Other regions are dispersed before gravity can complete the process. Feedback is the name given to this exchange between stars and the material around them. It can encourage star formation in one place while ending it in another. A shock front may compress a cloud edge enough to create dense cores. The same radiation field may later evaporate those cores or remove the gas that would have fed them. There is no simple division between creation and destruction. The same expanding bubble can do both. Massive stars have the strongest influence. They emit intense ultraviolet radiation and powerful stellar winds. They form quickly, live briefly, and may explode as supernovae, while lower mass stars from the same region are still young. Their deaths return energy and newly formed elements to interstellar space. A supernova shock can travel through the cloud complex that produced the star. It may heat gas to extreme temperatures, accelerate cosmic rays, destroy dust grains, compress distant material, and open a cavity that remains long after the original star has disappeared. The cloud gives material to the star. The star returns material to the cloud. But what comes back is not identical to what went in. Inside the star, nuclear reactions have built new elements. Stellar winds may carry some of them outward before the final explosion. The supernova releases more, adding oxygen, silicon, iron, and other products to the surrounding medium. Later clouds inherit this enriched mixture. The process is not perfectly efficient. Only a fraction of a molecular cloud's mass becomes stars before feedback disperses the remaining gas. Much of the material returns to the diffuse interstellar medium. Some may enter another cloud millions of years later. Some may rise above the galactic disk before cooling and falling back. Star formation is one passage through a longer circulation. The atoms entering a protostar do not share a single origin. Some may have remained in diffuse gas for ages. Some were expelled by aging stars. Some passed through earlier molecular clouds without joining a star. Some were once part of stars that no longer exist. The newborn system gathers these histories without preserving most of their boundaries. Inside the disk, grains from different sources mix. Heat alters their minerals. Ices evaporate near the star and remain frozen farther away. Material moves inward, outward, and across the disk before settling into larger bodies. A planet may form from matter that reached the cloud by many routes. Its iron may come from one generation of stars. Its carbon may have passed through several. Its water may include oxygen atoms created in stellar interiors and hydrogen that began in the early universe. The interstellar medium brings these materials into the same place. This is how the space between stars becomes more than a separation. It acts as a reservoir, a transport system, and a place of transformation. It holds what old stars release until gravity gathers some of it again. It cools matter, mixes it, protects molecules, and carries the chemical record of earlier generations into new ones. Long before a planet has an ocean or a surface, its ingredients move through these clouds. Long before a star shines steadily, its mass is spread across a region where atoms may wait millions of years between one stage and the next. The waiting is not empty. Gas is cooling, dust is changing, molecules are forming, gravity is measuring the balance, and somewhere inside the cloud, a center begins to hold. What leaves a star does not remain near it forever. Material released by stellar winds and explosions enters a larger circulation, one that can carry atoms across hundreds or thousands of light years before they become part of another cloud. Some of that matter moves through the thin disk of the Milky Way. Some is lifted far above it. Some escapes a star-forming region only to return much later from a different direction. The galaxy is not merely forming stars from gas. It is continually receiving gas back from them. A star similar to the Sun spends most of its life holding its outer layers close. Hydrogen fuses in the core, pressure supports the star, and only a comparatively light wind escapes into space. Near the end of its life, that balance changes. The star expands. Its outer atmosphere becomes extended and loosely bound. Pulsations move through it. Dust forms in the cooler layers, and radiation pushes on those grains, helping carry gas outward. Over time, a substantial part of the star can be returned to interstellar space. This outflow is not explosive, in the way a supernova is explosive. It may continue for hundreds of thousands of years, building a broad envelope around the aging star. Carbon, nitrogen, oxygen, and newly formed dust grains enter the surrounding medium at speeds far below those of supernova debris, but in quantities large enough to matter. The remaining core eventually becomes a white dwarf. The expelled atmosphere continues outward, thinning as it mixes with older interstellar gas. For a brief interval, ultraviolet radiation from the exposed core illuminates the material, producing what astronomers call a planetary nebula. The name is historical. No planet is required. Through a telescope, early observers saw small rounded forms that resembled planetary disks. In physical terms, these nebulae are the released outer layers of dying stars, shaped by winds, magnetic effects, rotation and interactions between slower and faster phases of mass loss. Their visible forms do not last long by stellar standards. After tens of thousands of years, the expanding gas becomes too diffuse to glow brightly. The nebula fades, but its material remains. It merges into the interstellar medium, carrying elements and dust into the wider galaxy. More massive stars return matter by a different route. Their winds can be strong throughout their short lives. Radiation pressure and energetic outflows remove surface material, sometimes exposing deeper layers that have already been altered by nuclear reactions. The star may lose several times the mass of the Sun before its final collapse. Then the supernova sends another wave outward. The explosion produces a rapidly expanding shock that sweeps into the surrounding medium. At first, the ejected material moves almost freely. Soon it gathers enough interstellar gas to slow down, transferring energy into the larger environment. Behind the shock, temperatures rise sharply. Atoms lose electrons. Dust grains are heated, damaged, or destroyed. Magnetic fields are compressed. Particles are accelerated. Gas that had occupied one phase of the interstellar medium is forced into another. The remnant grows. Over thousands of years, it can reach across many light years. The shock becomes slower, and radiative cooling becomes more effective. material accumulates in a denser shell, while the interior remains hot and rarefied. Eventually, the remnant loses its clear identity. Its shell fragments. Its interior merges with other cavities. Turbulence carries the remaining energy into smaller motion. The explosion has ended as an observable object, but its influence continues within the temperature, chemistry, and structure of the surrounding gas. One supernova can reshape a region. Many supernovae can reshape a large part of the galactic disk. Massive stars are often born in groups. Their winds begin clearing the surrounding cloud before the first explosion occurs. As the most massive members die, their remnants expand into a region that has already been disturbed and thinned. Later explosions encounter the same cavity. Their shocks can travel farther before slowing, adding heat and pressure to the interior. Over time, the overlapping activity creates a superbubble, an enormous volume of hot gas surrounded by shells of cooler material. Some superbubbles extend across hundreds of light years. Their edges compress nearby gas. Their interiors glow faintly in X-rays. Their expanding shells may collide with other clouds or bubbles, creating new sheets and filaments. If enough energy is released, the bubble can break through the thin layer of the galactic disk. The hot gas inside is less dense than the cooler material around it. It rises away from the midplane, carrying energy and enriched matter into the region above the galaxy's main star-forming layer. This upward movement is part of what is often called a galactic fountain. Gas leaves the disk without necessarily escaping the Milky Way. As it travels farther from the regions of concentrated starlight and supernova activity, it expands and cools. It may mix with material surrounding the galaxy. Gravity eventually draws part of it back. The returning gas does not descend as a single continuous rain. It may appear in clouds, filaments, and complex streams, and some moves at velocities that do not match the simple rotation of the galactic disk. Astronomers detect it through radio emission from neutral hydrogen, ultraviolet absorption in the light of distant sources, and other spectral tracers. These returning flows bring material back toward regions where stars can form. The cycle is not closed perfectly. Some gas may reach the outer halo and remain there for long periods. Some may be expelled more forcefully and escape the galaxy. Fresh material can also enter from outside, drawn from the circumgalactic medium, or supplied through interactions with smaller galaxies. The Milky Way exchanges with its surroundings. Its interstellar medium is therefore part of a system larger than the visible disk. Gas moves from stars into clouds, from clouds into stars, from the disk into the halo, and from the halo back toward the disk. Each passage changes it. Heavy elements become more abundant over generations because stars manufacture them and return a portion to space. Astronomers use the word metals for elements heavier than helium, even when those elements would not be called metals in ordinary chemistry. A cloud containing more of these elements can cool differently from a cloud made almost entirely of hydrogen and helium. Carbon and oxygen provide important cooling lines. Silicon, magnesium, iron, and carbon contribute to dust. More dust changes how radiation is absorbed, how molecules form, and how cold the cloud interior can become. The chemistry of later star formation is therefore influenced by earlier stars. The first generations in the universe formed from material with almost no heavy elements. The Milky Way today forms stars from gas that has been enriched repeatedly. The degree of enrichment varies by location, age, and history, but no nearby star-forming cloud is chemically isolated from the generations before it. This inheritance can be read in starlight. A star preserves much of the chemical composition of the gas from which it formed. By measuring absorption lines in its spectrum, astronomers estimate the abundance of iron and other elements in its atmosphere. Older populations often contain fewer heavy elements than younger ones. though the pattern includes many exceptions because the galaxy has mixed, migrated, accreted material, and formed stars at different rates in different places. Chemical abundance becomes a kind of ancestry. Groups of stars with similar compositions may share a common formation environment, even after their motions have separated them. Large stellar surveys compare many elements at once, looking for patterns that reveal where stars may have formed and how they travel through the galaxy. The interstellar medium is the link between those generations. It receives the products of one era and becomes the starting material of another. The mixing is not immediate. Fresh supernova debris does not spread evenly through the Milky Way in a single event. It moves through a structured environment, entering hot bubbles, cooling shells, diffuse gas, and molecular clouds at different rates. Some elements may remain concentrated locally for long periods before turbulence, and large-scale flows distribute them more widely. A new star can therefore inherit material from a mixture that is broadly galactic, but locally uneven. One cloud may have been touched by the remains of several supernovae, the winds of aging stars, and gas returning from the halo. Another cloud nearby may have experienced a different sequence. The galaxy recycles, but it does not blend everything into uniformity. That incomplete mixing preserves information. Meteorites contain isotopic patterns that point towards several stellar sources. Starlight records the chemical history of birth clouds. Interstellar absorption lines reveal material currently between systems. Together, these traces show that the cycle is real, without requiring every step to be observed in one place. No single human lifetime can follow an atom through the full route. A particle leaving an aging star may spend millions of years in diffuse gas. It may be swept into a super bubble, carried above the disk, cooled into a returning cloud, and later drawn into a molecular region. It may join another star. It may remain in a disk. It may become part of a planet and stay there through billions of orbit. Across that span, the atom has no memory in the human sense. Yet its isotopes, its chemical bonds, and the structures it joins preserve parts of the journey. The Milky Way has been repeating this exchange for most of its life. Stars appear to be separate objects, each surrounded by its own darkness. But their material moves beyond those boundaries. One generation alters the clouds of the next. A star that died far away can contribute to a system formed much later, in a region that did not yet exist when the original star began to shine. The distance between stars does not prevent connection. It is where the connection travels. The circulation of the galaxy continues through the place where the solar system is moving now. The sun is not resting inside a fixed pocket of space. It travels around the center of the Milky Way, while nearby stars follow their own paths. Around the sun, the interstellar medium also moves, carrying gas, dust, magnetic fields, and energetic particles through the local stellar neighborhood. For most of daily life, this motion leaves no visible sign. Atmosphere. Earth's magnetic field deflects many charged particles. The solar wind fills the space around the planets with material flowing outward from the sun. Yet beyond the familiar boundaries of air and magnetism, the solar system is immersed in a larger flow. The sun continually releases plasma from its outer atmosphere. Electrons and atomic nuclei stream past the planets at hundreds of kilometers per second. This solar wind carries the sun's magnetic field with it, creating an enormous region known as the heliosphere. The heliosphere is not a perfect sphere. The sun moves relative to the interstellar gas around it. The external magnetic field is tilted. The solar wind changes with the sun's activity. Charged particles exchange energy near the boundary, and neutral atoms can pass through regions that charged particles cannot cross as easily. The result is a changing structure shaped by two environments meeting. From inside, The solar wind pushes outward from outside interstellar plasma, magnetic pressure, neutral gas, and cosmic rays press inward. Where the outward solar wind can no longer expand freely, it begins to slow. Farther away lies the heliopause, the broad boundary where the influence of the solar wind gives way to the surrounding interstellar medium. This boundary is not a solid surface. No spacecraft strikes it like a wall. Instead, instruments record gradual changes. Particles associated with the solar wind become scarce. The magnetic environment shifts. Galactic cosmic rays become more abundant. The surrounding plasma carries different properties from the material flowing out of the Sun. Voyager 1 and Voyager 2 eventually crossed this boundary in different directions. They had been launched to explore the giant planets, not to map the edge of the heliosphere. Their extended journeys transformed them into the first spacecraft to sample the local interstellar environment directly. Even there, they remain close to the Sun by galactic standards. The nearest stars are light years away. The Voyagers have traveled for decades and crossed only a small fraction of that distance. They are in interstellar space because they have moved beyond the heliopause, not because they have left the Sun's broader gravitational neighborhood or entered the vicinity of another star. The distinction reveals how many boundaries can occupy the same region. The heliopause marks the end of the solar wind's dominance. The distant comet reservoir surrounding the solar system extends much farther. The Sun's gravity continues beyond both, and the local interstellar cloud through which the heliosphere moves is itself only one small structure inside the local bubble. A boundary depends on what is being measured. For charged solar particles, one edge matters. For long-period comets, another matters. For starlight, gravity, dust, and neutral atoms, the useful divisions are different again. Some interstellar atoms enter the heliosphere without being strongly deflected. Neutral hydrogen, helium, oxygen, and other atoms carry no net electric charge. They do not spiral around magnetic field lines in the same way that charged particles do. Some pass through the outer boundary and continue inward, forming a faint stream through the planetary system. Many are altered along the way. Ultraviolet radiation from the Sun can remove electrons. Charge exchange reactions can occur when a neutral atom passes near an ion from the solar wind. Once ionized, the former interstellar atom becomes responsive to the solar magnetic field. The solar wind can then carry it outward again. These particles are called pickup ions because they are gathered into the solar wind after entering from neutral interstellar gas. Their motions preserve information about the material outside the heliosphere. A small part of the interstellar medium enters the solar system, changes state, and leaves embedded in a solar flow. Dust follows another route. Interstellar grains, large enough to resist complete deflection, can pass through the heliosphere. Spacecraft instruments have detected particles whose speeds and directions distinguish them from dust already bound to the solar system. These grains are microscopic visitors. They may have formed around stars that were never near the Sun. They may have crossed changing clouds, survived shocks, and wandered through the local galactic environment before entering the region between the planets. Their passage is brief compared with their earlier journey. Solar gravity bends their paths. Radiation pressure pushes against them. Electric charge acquired from sunlight and plasma allows the magnetic field to influence them. Depending on their size and composition, some are filtered near the heliosphere's edge, while others travel deeper inward. The stream is sparse. No visible haze forms around Earth. The particles are detected one by one through tiny impacts and careful measurements. Yet each grain is direct evidence that the solar system is open to its surroundings. The boundary reduces and redirects the flow. It does not isolate us completely. Galactic cosmic rays also test this boundary. These high-energy particles arrive from beyond the solar system. Many have traveled through magnetic fields for so long that their original directions have been obscured. As they approach the heliosphere, the solar wind and its magnetic field scatter and slow some of them. Their intensity near Earth changes with solar activity. When the sun's magnetic influence is stronger and more disturbed, fewer lower-energy galactic cosmic rays reach the inner solar system. During less active intervals, the shielding weakens and more can enter. The heliosphere therefore acts as a changing filter. It does not block every cosmic ray. The most energetic particles pass through with little difficulty. But the local radiation environment around the planets is shaped partly by conditions near a boundary billions of kilometers away. This protective effect depends on the external medium as well. The Sun is currently moving through warm, thin, interstellar material. In a denser environment, the pressure outside the heliosphere would be greater, and the boundary could contract. In a thinner region, it could expand. Over the Sun's history, the surrounding conditions have not remained the same. As the solar system travels through the Milky Way, it crosses cloud edges, cavities, and flows created by older stellar activity. These changes unfold over timescales far longer than recorded history. There is no reason to imagine each crossing as a sudden event. A diffuse cloud does not always have a sharp surface. Density may increase gradually. Magnetic orientation may change across a broad region. The mixture of neutral and ionized gas can shift over thousands of years. The heliosphere responds as it moves. Its outer shape adjusts. The filtering of particles changes. The stream of neutral atoms takes on different properties. The solar system carries its internal rhythm of solar cycles through an external environment that also changes. This interaction leaves faint records. Certain radioactive isotopes found in ocean sediments and lunar material have been linked to supernova debris that reached the solar system in the past. The explosions occurred far enough away to avoid destroying life on Earth, yet close enough for some of their material to cross interstellar space and arrive here. Atoms made or released in distant stellar deaths settled onto a planet already filled with life. Their presence connects geological layers with events among nearby stars. The amount is small, but the root is immense. A shock passes through interstellar gas. Dust grains carrying rare isotopes move outward. Some survive the crossing. Some penetrate the heliosphere. A fraction reaches Earth and becomes part of the seafloor. Millions of years later, human instruments identify the signature. The space between stars has entered the geological record. Earth itself returns materials outward. Atmospheric particles escape slowly. Dust from asteroids and comets moves through the planetary system. Spacecraft leave on paths that may eventually carry them far from the Sun. But the mass moving outward from the planets is slight compared with the continuous solar wind. The Sun is the dominant local source. Every second it releases charged particles into the heliosphere. Much of that material eventually approaches the outer boundary, interacts with the interstellar medium, and contributes energy and magnetic structure to the surrounding region. The Sun is therefore both a traveler through the galactic environment and a source within it. It receives neutral atoms, dust, and cosmic rays from outside. It sends plasma and radiation outward. Its boundary is made from that exchange. The same is true around other stars. Many stars produce winds and surrounding cavities. Some are weak and compact. Others are powerful enough to sculpt large bubbles. A star moving rapidly through gas may create a curved region ahead of its motion where the surrounding material is compressed. Across the galaxy, stellar systems carry their own local environments through the larger medium. The space between them is not separate from the stars. It is continually shaped by what the stars release, and the stars are continually shaped by what surrounds them. From Earth, the night still appears divided into lights and gaps, but the solar system is already moving through one of those gaps, enclosed by a solar wind, crossed by interstellar atoms, and touched by particles that began far beyond the planets. The darkness between the stars is not somewhere outside our neighborhood. It is flowing past us now. Far from any single cloud or star, the larger pattern becomes easier to see. The material between stars is always being exchanged. Gas leaves aging stars and enters diffuse space. Shock waves gather some of it in two shells. Turbulence breaks those shells into smaller structures. Cooling allows denser regions to form. Dust helps molecules assemble. Gravity draws selected parts inward. Stars and planets emerge, and the remaining material is scattered again. No stage stands apart from the others. A molecular cloud is connected to the stars that enriched it. A young stellar system is connected to the diffuse gas from which its cloud formed. A supernova remnant is connected to future clouds that may not gather for millions of years. The distances are large, but the physical chain is continuous. Hydrogen provides the oldest part of that chain. Much of it was created during the early history of the universe, before galaxies, stars, or planets existed. Since then, hydrogen atoms have moved through countless environments without losing their identity. Some entered the first generations of stars. Some remained in diffuse gas. Some joined molecules inside dark clouds, became part of new stars, and were later returned to space. The heavier elements followed a different path. Carbon, oxygen, silicon, and many others were made within stars or during stellar explosions. They entered interstellar space only after stars began changing the chemical composition of the universe. From that point onward, every new generation formed from a mixture shaped by earlier ones. The Milky Way still carries that mixture now. It is present in the dust-crossing dark clouds, in the calcium-absorbing starlight, in the carbon monoxide revealing molecular gas, and in the iron held inside planets. The interstellar medium preserves no complete record of where each atom has been. Mixing gravity between one source and another, a cloud may contain material from many stellar winds and explosions, along with hydrogen that has never passed through a star. When gravity gathers the cloud, these histories enter the same collapsing region. A new system begins without a single beginning. Its matter arrives from different times. The Sun formed from such a mixture before the solar system existed. Its material belonged to the interstellar medium of the Milky Way. The cloud that gave rise to the Sun contained hydrogen and helium, heavier elements made by older stars, and dust grains that had already survived long journeys. Most of the original cloud did not become part of the Sun. Some entered planets and smaller bodies. Some was pushed away during formation. Some remained in the surrounding region and continued through the galaxy. Even within the solar system, the distribution kept changing. Material collided, melted, rose, and moved between orbits. Planets gathered different proportions of rock, metal, gas, and ice. Small bodies preserved fragments of earlier stages. The interstellar journey did not end when the Sun began to shine. It changed scale. The atoms inside Earth became part of oceans, minerals, atmosphere, and life. They moved through chemical cycles far faster than the galactic cycle that brought them here. Carbon crossed from air into water, stone, and living cells. Oxygen entered minerals and later moved through the atmosphere. Iron settled deep within the planet and helped create the magnetic environment surrounding it. These local changes are brief when compared with the time between stars. A human body holds its atoms for only a short interval. Earth may hold them for billions of years. The galaxy may carry them through changing environments for far longer. Nothing in this comparison reduces the importance of the present form. It places that form within a wider continuity. The matter around you is not visiting from another universe. It belongs to the same physical history as the stars overhead, the clouds hidden within the Milky Way, and the dust entering the heliosphere. The connection is material rather than symbolic. Spectroscopy measures it. Meteorites preserve it. Spacecraft sample it. Radio telescopes map it across the galaxy. The space between stars can seem remote because it cannot be touched in an ordinary way. Yet parts of it enter the solar system as neutral atoms, cosmic rays, and dust. Other parts entered long ago and became the substance of the planets. The separation is one of distance and time, not composition. The Milky Way continues to change around us. Stars are forming in cold clouds. Older stars are losing their outer layers. Supernova remnants are expanding. Hot gas is rising above the disk. Cooler material is returning. Magnetic fields are bending with the flow. None of these processes requires the galaxy to move toward a final arrangement. The interstellar medium is maintained by change. If every cloud collapsed, diffuse gas would disappear. If stars returned no matter to space, the supply for later generations would decline. If energy were not carried outward by radiation, winds, and explosions, the structure of the galactic disk would be different. The familiar Milky Way exists partly because matter is never held in one place forever. Even stars, which seem permanent during a human lifetime, participate only temporarily. A star gathers interstellar material, holds part of it for millions or billions of years, alters some of it, and releases a portion back into the galaxy. The star is a stage in the circulation rather than its destination. The same is true of planetary systems. Their formation removes material from interstellar space, but not beyond all return. Stars shed mass, orbits are disturbed, comets are scattered, planets can lose atmospheres. When a star reaches the end of its life, the architecture around it may change again. Some matter remains locked in faint stellar remnants or cold bodies for immense periods. Other matter resumes its movement sooner. The cycle has no single pace. A cosmic ray crosses a cloud quickly. A dust grain may wander for millions of years. Gas in a hot cavity may travel far above the galactic disk before returning. An atom inside a small planet may remain nearly fixed through much of the life of its star. All belong to the same galaxy, but each follows a different clock. This is why the space between stars cannot be understood as one empty interval. It is a collection of paths. Some paths carry energy, some carry newly formed elements, some carry magnetic disturbances, molecular chemistry, dust, or radiation. Some eventually lead into the centers of collapsing clouds. The paths cross without becoming visible to the eye. A dark lane in the Milky Way may contain gas arriving from older stellar generations. A nearby hot cavity may have been shaped by explosions whose stars have vanished. A stream of interstellar atoms passing the sun may belong to a cloud that will continue onward long after the solar system has left it behind. The night sky shows only a thin projection of this movement. Stars appear fixed against blackness because their changes are slow and their distances flatten the view. The clouds between them may be almost invisible. Their motion may require generations of observation to detect. But the still image is not false. It is simply brief. For one night, the stars hold their positions closely enough to guide a traveler. For one lifetime, the Milky Way keeps its familiar shape. Beneath that appearance, gas flows, fields turn, particles scatter, and clouds gather. The galaxy does not need to display its motion quickly for the motion to be real. Somewhere now, a hydrogen atom is entering a colder region. A dust grain is acquiring a layer of ice. A shock is losing energy as it crosses a cloud. A molecular core is becoming dense enough for gravity to strengthen. None of these events announces that a future star has begun. They are small transitions within a process that may take millions of years to become luminous. Long before the first light appears, the preparation is already underway. And after that light fades, the material will continue. Between the stars, the galaxy keeps passing its matter onward.